All right, this is problem 14.4. It's on page 598. A 15,000-pound plane lands on the deck of an aircraft carrier at a speed of 125 miles per hour relative to the carrier and is brought to a stop in 2.8 seconds. Determine the average horizontal force exerted by the carrier on the plane, A, if the carrier is at rest, and B, if the carrier is moving at a speed of 18 knots in the same direction as the airplane. All right, now there's some interpretation to this problem. The answer in the back of the book, in my opinion, is wrong because they say it's the same force. But if the carrier is moving at the speed given in part B and continues to move at that speed, then it would take less force to bring the plane to rest. I mean, in a limit, think of the plane and the carrier moving at essentially the same speed. It really wouldn't take much force at all, or any force, to land the two together. Obviously, the carrier can't move at the same speed as the plane, but it wouldn't take any force to decelerate the plane to the speed of the carrier if they were going the same speed. So anyway, the mass of the plane that's given is 15,000 pound mass. The initial velocity is 125 miles per hour, which comes out to about 183.33 feet per second. If you don't know how I did that, you should pause the video and try the unit conversions. There are unit conversions in the back of your book. You should be able to get to this without too much trouble. For part A, the velocity of the carrier is 0, but for part B, the velocity of the carrier is 18 knots. Now, converting the 18 knots to miles per hour, or excuse me, to feet per second, is just one more step. You just need to convert the knots to miles per hour. That conversion factor should be in your book as well, and I won't belabor the point. You come out with, or you should, 30.4128 feet per second. So it's the relative velocity between the two that's important. Initially, the relative velocity is 183. For part B, the relative velocity is about 153. Okay, so our solution for part A, oh, by the way, the amount of time, delta t, for landing the plane is 2.8 seconds. Okay, so anyway, our solution is to use momentum balance. The initial momentum plus the integral over time of the force acting on the plane is equal to the final momentum. Now this will be 0, of course, in part A. And so since the force we're assuming is an average force, that would be a constant force that comes out. So the average force, if you solve for it, comes out to the initial momentum divided by the amount of time required to land the plane. Now, I'm not being very careful with my signs. The direction of the velocity would be in the positive direction, for example, and the force would be in the negative direction, so I should have a negative sign in here somewhere if I'm thinking right. Let's see. We move that to the other side. So I'm not terribly worried about the fact. I just know that the force will be in the opposite direction of the velocity, and I'm just looking for its magnitude. So I'm not going to bother with the sign in this problem. So 15,000 pound mass multiplied by an initial velocity of 183.33 feet per second divided by 2.8 seconds. We need a conversion factor because pound mass foot per second squared is a valid unit of force. However, it is not pound force. There's a difference between the two. Let's do it this way. 32.2 pound mass feet per second squared is 1 pound force. Okay, so that takes care of the pound mass, the feet, and the second squared, and we're left with pounds force. So the amount of force required for part A, the average force, is about 30,501 pound force. That's how much force is required to bring the aircraft to a halt. Now for part B, things are a bit different because the final momentum of the plane is not 0. The final momentum of the plane is the mass of the plane multiplied by the velocity of the carrier, because now the plane is moving at the velocity of the carrier. So then this term is no longer 0 in part B. In fact, what you'd have is mv naught plus, let me just write average force because it's going to come out again, delta t equals mvf, where vf is the final velocity of the plane, which is just the velocity of the carrier. And so if we land the plane in the same 2.8 seconds, rearranging and solving for the average force, once again not being terribly particular about the signs, you'd have mass multiplied by v naught less vf divided by delta t. Now I've included a negative sign in here that I'm just skipping because I know the direction of the force, like I said, and it's opposite the direction of these velocities. Anyway, I just need the magnitude. So 15,000 pound mass multiplied by 183.33 less the speed of the carrier, 30.41 or so feet per second, divided by 2.8 seconds multiplied by 32.2 pound mass feet per second squared per 1 pound force. Once again, everything goes away except for the pounds force. And the amount of force required in case B is about 25,442 pounds of force, which is 5,000 pounds less. That's what, 2.5 tons less force or so, approximately. So that's a significant difference.